Put it. So hello everyone. This is a bit late coming of our seminar today with the big return of Vysoký, who will say something what will resume what he told us last time. And yeah, because we are in a hurry, I will stop at this moment.
Okay, thank you for the introduction. So welcome back, everyone. Thank you for coming back also. So just to remind you very quickly, last time I have introduced the space of differential operators of order K on some gradient vector bundle over some open subset U. So this was some space of maps of sections of the gradient vector bundle with some properties which we discussed last time. And I promised you to justify the name K order differential operator. So why should be these guys called differential operators in the first place? And this is because they locally look like differential operators. So I have to work locally. So now I have some gradient local chart for my manifold curly N. And therefore, I have some set of local coordinates. So I have some local coordinates, Z, A, labeled from 1 to N. So I have some local coordinates. And then I also, because I'm working with gradient vector bundle, I want it to be trivial over this open subset U. So I assume that I have some local frame for my gradient vector bundle. So I have numbers from 1 to R, where R is total rank of my gradient vector bundle, and this is local frame. Or over this open subset U. So I assume that I have these two things. And then I have to introduce a little bit of notation. So that now comes just the notational part. So first of all, I have to consider some special subset of n indices, which I denote as this n bar n. And this will be n indices. So there will be n integers, and these integers will be non-negative. So this is n0 to the power of n. And I only impose certain condition on those n indices. And this condition is that each of them has to be only in the set 0, 1 if the degree of the corresponding coordinate dA is odd. So this may look like a little bit strange condition, but this condition is just tailored so that if I take Z and I denote it, sorry, I denote those guys as set I. So Z set I simply means that I take Z1 to the power of I1, Z2 to the power of I2, this double thing. And then I continue and I take Zn to the power of In. And this condition simply gives me that this is non-zero thing. Okay? Because if I would draw this condition, then Z to the power of something bigger than 1 will be 0 because the power of odd coordinate is always 0, except for the case 0 or 1. So I only choose this condition to this be true. Okay, then I have to introduce the notion of weight of such an index, and the weight of such an index is just the sum of all of them. So this is some non-negative integer. And then subset, just a notation, subset n bar and q, which consists of all n indices in n bar and such that they have given weight. So this set contains all n indices on non-negative integers satisfying this condition plus the condition that some of them is q. And this is almost it. And finally, I introduce a notation that q, and this is just an q. Sorry, this is q index consisting of I1. There's I1 times, there is Z1, then I2 times, then there is Z2, and you end up with Zn2. And this is defined for all I from this set n and q. Right? So this is just the distinction between these two guys. This is just a product of all these monomials to respective powers ordered in this special way, and this is just V1 to the power of monomial. And that's finally, okay. So my last piece of notation I need. So I need to construct operator of iterative partial derivative. So I denote this as gi. So to each I then this kind of operator, and there is this with a subscript like opposite, because kind of contrary what you would expect, I start from Zn. So I take partial derivatives along Zn to the power of In, and then I continue to d over g Z1 to the power of I1 and In. And compose all these partial derivatives with respect to coordinates acting on my function. And this is met on functions of degree, and the degree of this operator acting is minus z to the power of I, where this is this product here, right? If you look at the degree of this monomial, it's I1 times degree of Z1 plus I2 times degree of Z2, etc. And it's exactly the degree of this operator, and it's minus because we are partially differentiating coordinates out of it. So, okay, and now comes the main theorem. So how all these French notation things are used to describe differential operator. So this is just theorem, and this is in fact the only difficult thing about all these differential operators. To prove this is that if you take G, which is a differential operator of degree K, sorry, I call it order K on E over U, where U is domain for local charge and for local frame, so I can work locally. Then D can be uniquely G or Q of G uniquely decomposed as D, and you sum over basically our order of derivatives from Q to K. Then you sum over these n indices from this set and Q. And then there is some factor, 1 over I factorial, which I will describe in a moment. And then there is D. There are some coefficients, which I will describe later. Now the mu. And then there is some basis of operators, which I will give this pi, so P. And then you have index I, and then me, and then dot. And what are these functions? Where this fat, it should be fat D, fat I, mu lambda. There are just some functions on U, on my manifold, and they are obtained from so what you do, you take D and calculate this iterated commutator, which I did last time, whereas a q-tuple of function, you use this q-tuple of functions there. And this is just some operator, and you apply it on phi lambda, which is a section. So you obtain again some section and coefficients of this section are these functions. So this basically, you just have to calculate iterated commutators of your D with coordinate functions, with this lambda of coordinate functions, apply the resulting operation on phi lambda, and you obtain some functions which then play the role here. And these operators, these phi lambda I mu, they act on sections because they are operators, and they act on each section. So because phi lambda is a local frame, so you can decompose each section uniquely using some functions. And these operators, and I should maybe use some different summation index here. And then basically what they do, they calculate something like, there's some plus minus sign. And then you act by this differential operator di op, which is here, on psi lambda. And this is some function, and you multiply it by phi mu. So basically, what every differential operator does, it's just some combination of iterated partial derivatives. And the coefficients of this combination can be obtained by this formula uniquely. And this time here is also kind of easy, but I simply didn't want to write it down. And this is kind of the basis of differential operators. And what this proves, this theorem, what does it prove? It proves that, in fact, this FKEU is freely and finitely generated, because these operators, you have to prove that, but it's almost clear that this P lambda I mu are in fact differential operators of order on E over U, and these form set of generators for this E U. So, and it's freely generated, so because the decomposition is unique, and it's finite set because there's finitely many of them. And this summation here over my mu lambda is finitely many of them, and this number of n indices here is also finite because they are up to some givens. Some of them is some given number to non-negative integers. And so this justifies the word why it's called differential operators. This gives you some nice formula how to expand it using this local frame, and it also proves that this diff k is a sheaf of sections, because immediately you can see if it's freely and finitely generated, it has to be sheaf, because you have it is sheaf. So you know from the beginning that it's a sheaf, but it's a sheaf of sections of, I noted this J, G, K, E, and call it the gradient vector bundle of case order differential operators. This is the integrated bundle of case order differential. This on E. So this kind of concludes my first part. So I was able to prove that differential operators are locally free and finitely generated. Therefore, they form a sheaf of sections of some graded vector bounding, which I did not validate. Now I can go to graded jet bundles. So this is the first master for it. So say I want to erase my board. And I will be erasing, so let me just comment on this next part. So for me, graded vector bundles are sheaf of sections, right? That's what we learned last time. So if I want to define graded jet bundle, I kind of have to define it using its sheaf of sections. So I have to find the sheaf of sections of graded jet bundle directly. Also, if you try to mimic the standard construction of jet bundles, so you take jet space at each point, which is some equivalence classes of some equivalence relation. When you say that two sections are equivalent, if they have case order contact at 0 or something like that, it fails because it's not a good idea to compare values of sections at points in the graded setting, because by looking at values of sections, you lose a lot of information on them, and you are not able to get anything meaningful out of it. So you have to really work and algebraic. And luckily, there is an algebraic description of sections of graded of ordinary jet bundles, which you can find in a book by someone. And here written Vysoký and Minoguer's book, which is called Geometry of Jet Spaces and Nonlinear Partial Differential Equations. So basically, I'm stealing their description of jet bundles. The difference is that they do it on the level of vector space of global sections. So they don't really talk about sheaves at all, because they simply use this self-sum theorem saying that you just have to study the space of sections and prove that it's projective module finitely generated, and then you are finished. We cannot do this here, so we really have to talk about sheaves, which brings some slight technical difficulties, but can be overcome. So, So now I will talk about graded jet bundles. And I will take you through the construction, model some technical details. So what you do, so you take open subset of your N. And what can you do first? You construct space X of U. There's no reason to call it X, I just call it X. And you take tensor product of functions with sections. But you take the product over R, so this is no trivial thing. This guy here is in fact graded module. This is graded C infinity curly M U module. And in fact, there are two module structures here. First of them, so I take function and I will use empty triangle to denote it. So generators of this space are tensor products of some function and of some section. And to define these two and you are using the structure of algebra on the graded functions. So this is the first module structure you have. And then there's a second one, which I denote by full triangle. This one maybe not the best idea. Which on the other hand uses the module structure on sections. So there's some just fun sign because you are taking F through G. There's some sign, and you need GB, and here you take F times psi, where this is the module structure on the space of sections. So you have two different actions at your disposal, and they are not the same, right? There's no reason why they should be the same. So you compare them. So you define delta F to be just be the difference of left translations of these two actions. So explicitly, df on h times psi is what f times h times psi minus 1 to f g h psi. So define this kind of map. Interestingly, this map is linear with respect to both actions. Kind of nice, but it's true. But if they would be same, this would be 0, but they are not in general, right? And what you can do, you can now construct a graded subspace of this space, which I know as V, and it now depends on some integer k. And this is just a graded subspace generated by iterated actions of this map delta. So I take df1, delta f1, delta k plus 1, and there's k plus 1 of them acting on h and the psi. And I go through all combinations of functions on n review and through all sections. And I take set of all of these things and produce graded vector space out of it. So kind of 3 vector space generated by the set. And this is some subspace of mine. So this is some subspace for this x, how I write it, different x. U. And in fact, this guy is not only a subspace, it's a infinite M submodule with respect to both triangles. So this guy here is infinity M U submodule with respect to both triangles. And this is kind of easy to see because I told you that this delta F map is linear with respect to both actions. So to act with some linear combination of these guys, then you can go with the function inside. And you are finished. Okay. And therefore, you can construct quotient module out of these two. So you can construct, that's the next step. You can construct, I call it a P. That's intentional P here because it will mean free sheaf, because it will not be sheaf. But I can construct this. It's just a simple M module at this moment. I simply quotient out this subspace, sum of all of this, right? And if you take a quotient of graded module by its submodule, it's again module without no problem. So this is subgraded infinity mu module. And there are again two actions of thinking and view, because right, I have two actions here. This is some module with respect to both of triangles, so I have both induced triangles here. So with two actions, which I denote in the same way. So I do not add any primes or heads or tildes or anything. I just use the step symbol for the original action for the induced action. And okay, what's the notation? Of course, I have quotient map from here to here. So I will just use the notation that H tensor with little subscript k here is equivalent class of the corresponding guy upstairs. So this is, let's denote the quotient map as nature of k, and this is just an equivalent class of, this is my notation, so this is doubling here. And this of course generates this subspace. So I can define everything on generators, and I just have to verify something. Right. Okay. And of course, the ideal case scenario would be that this defines my sheaf of sections of jet bundle, right? So that's one note, that this P jet K E is in fact a presheaf of graded infinite and new modules. How are restrictions defined? You use obvious restrictions here. So here you have obvious restrictions, because on generators we simply restrict restricted sections using your restrictions here. This induces, of course, and this is then supersheaf, and those restrictions induce kind of obviously restrictions here, but there is no reason why this should be again a sheaf. I'm not claiming it is not, but there is no kind of a primary reason for it, because locally it is already a sheaf, but globally, yes, I'm not even sure about this. I don't think. Because now, there are no two technical difficulties with this guy. So in ideal case, this would be our sheaf of sections of our J1, and will be finished. And then there is first obstruction, which is the most interesting one. And unfortunately, I have no time to talk about it too much. But I will comment on it. Okay, so there are some difficulties. You would like this guy to be locally freely and finitely generated. So you try to do something, and it turns out that for it to be true, there has to be some submodule which is trivial. So there is some presheaf of submodules. I will be really later. There is some presheaf submodules which has to vanish, which should vanish. And there is some embarrassing thing now that there is no reason for it to vanish, but I have no examples proving that it does not vanish, right? So I believe you have to do this procedure, which I will now describe, but I'm not sure if you have to do it. But the good thing is that if this presheaf vanishes for some reasons, then this procedure which I will now describe does nothing. So you basically do something which fixes the problem if there is one, and it does nothing if there is no problem. So it's not a really big thing. And basically what you can do, you can take this presheaf of some modules and quotient it out. You simply take it and quotient it out, and it is not anymore in the quotient presheaf. So you are kind of safe. And if it vanishes and you quotient it out, you are safe, right? So you mod it out. Mod it out, or quotient it out. And this procedure is called, and I'm using the nomenclature from this book I was telling you about. And this procedure, I call it geometrization. And basically, there is some functor which I denote as geometrization functor, which goes from presheafs of C-infinite and modules to something which is called geometric, and this is the name they use in this book, geometric presheafs. And geometric presheafs are exactly those where this presheaf of submodules vanishes. So that's the definition, basically. And so what I do, I define another presheaf that I denote GPJ, G for geometric, and I simply geometrize my. In fact, the procedure is on modules, not on presheafs, so I simply take this module and quotient out this ugly submodule, and I end up something which is already geometric.
So can I ask, why do we need this quotients?
You have to do it because if you try to prove that this guy is locally freely and finitely generated, you fail. And if you do this procedure, that's exactly something which you have to declare zero is zero because it is in this presheaf, which I quotient out again. Anyway, so in this way, I kind of make sure that it works. But it's it's stupid excuse, but really I don't have any proof or counter example saying, okay, let's not, this procedure fails if you don't do it, but I'm simply not able to make another step in the proof without this procedure. So I do it, and in case this guy is already geometric, I'm safe. And why this is nice? Because in fact maps. So how big? Why this is safe? Because if you have any presheaf C-infinity M linear presheaf map from any so I use some presheaf map from any presheaf to geometric presheaf, so this G is geometric, then this functor is kind of universal in the sense that if G is geometric, then the element uniquely factorizes through its geometrization. So it's like with sheafification. So no, this should be non-dashed arrow. So there's some presheaf morphism into it. This is just the quotient map, basically, and every presheaf map into geometric presheaf vectorizes through its geometrization. So this is nice because you usually want to construct some maps, and you can construct those maps, and then you just use this universal property to obtain presheaf morphism from its geometrization to G. And why they are called geometric? Because sheets of sections of vector bundles are geometric. So if E is vector bundle, it's a vector bundle, then its sheet of section is geometric.
Does it mean that this sheet is representable? That you can find some representative object in.
I'm not sure. I'm not claiming anything like this. No, I'm not saying that every geometric presheaf is sheaf of sections of some relevant, but no. But sheaves of sections with the bundles are geometric. Okay, and there is another difficulty. There is no reason to think that this geometrization, so this GPZ, so if you start with presheaf, even when it's sheaf, then it's not clear that geometrization of it will be again sheaf. There's no reason to think that. So you have to make it into sheaf, and how you make things into sheaf, you sheafificate. So that's kind of cheap when you always use when you work with when you want to construct new sheets out of old sheet. You have to sheafify. Sheafify. Stupid word, in fact.
Or Spotify.
Okay, so this brings me to definition. So I define sheaf of cave order jets as I denote this as jet K, E, and I simply sheafify sheaf make it into sheaf of geometrization of my widget AB. So this is my sheaf of cave order jet. And okay, and so first of all, why this? So first of all, there is a way how to prove that you can use basically the same trick as for differential operators to prove that this guy is already locally, in fact, already this guy is locally free and finitely generated. So this is locally sheaf. So this guy locally is in fact just this guy. Globally not, but locally yes, because locally this is sheaf. So sheafification does nothing locally. So locally you can really work with this as this. And so again, I have some local chart and some local frame as before. And then what are my generators of my sheaf? So they look like this. So for any j in n, I define set delta, j, and there's some j tuple of functions, and there's index lambda here. And then I simply iteratively act by these deltas. Fj. And what I am acting on, I'm acting on one tensor with phi lambda. So this thing here is some element of this P jet K U. And then I take equivalence class in this quotient, which I did not, but for some reason I use big dot here. So this is just meaning that I will send it to the quotient by the quotient back. And this is my definition. So these are just some collection of objects in G, P, jet, K, E of U. And then I again use some notation the same as before. So this is I just take G, and then I take Q, and then I take this set I, Q, lambda for all set I in this N. So this is the same index set as before. So it's just less than to simplify a bit. And then what I'm claiming is that this is the most important statement, that you can express this thing. And there's a very similar sum. Okay, there is sum is that I and Q. Then there's just some sign plus minus. 1 over set I factorial, which I didn't explain before what it is, but it's basically just product of factorials of all these indices. Set I factorial is I1 factorial times I2 factorial times I3 factorial, blah blah blah. You get just that. And then there is iterated partial derivative of this psi lambdas. And then there are this triangle. And then there are this. So I can decompose this thing like this. And basically, this already proves that these guys form a set of generators, right? Because now, and with respect to this triangle, so this empty triangle will be my action which I use for my bundle. And these are the coefficients. So how do you calculate coefficient of this guy? You simply calculate all the iterative derivatives of these components of this psi, and then you multiply these things. And this proves that this is in fact finite set of generators for my GP jet KU. And so for U, which is coordinate chart, it's freely and finitely generated. Therefore, this guy is locally free and finitely generated. Therefore, it's a sheaf of sections of some great vector amount. So that's the main theorem. Okay, so everything is just a corollary of this thing. But I'm now fine because I have found myself a nice sheaf, which I call sheaf of sections of right-digit bundle. Some water for me. And of course, now comes obvious section, obvious question. Why? Why do I call this sheaf of sections of right-digit bundle, right? So I have to somehow justify that this is a good candidate for jet bundle. And this will be to conclude my talk. So why? Okay, so sorry, I just didn't write. No, it's not written like this. Core, blah, blah. 2 L's and R. Okay, so this jet E is the sheet of sections of great vector manual jet notice GA. Right? And this is called K or the jet manual. On this manual. Okay, so why? So first of all, in classical case, this gives you jet bundle due to Gaussian checking and maneuver. So they basically prove that they don't work with sheaves, but if you look at the global sections, they don't even have to geometrize and sheafify. They claim that this PJet KM is really isomorphic as a module to sheaf of sections of jet bundles. So in principle, in fact you don't have to sheafify whatever and geometrize whatever. For classical case it works automatically. So classically this gives you jet bundles. So that was of course necessary. Kind of. Then if you look at k equals 0, and in classical geometry J0 0 order jet bundle is just E, right? So you have to check that this is true here, but this is obvious, right? Because this V0 is just generated by sections of the form F times J times minus 1 and J times F psi. So you model by this relation. So you impose this relation, and then this GPJ, no, not G, just PJ, which is 0A U, is basically, if you look up the definitions, this is basically exactly what is called tensor product of these two guys over C infinite and U. Precisely the definition. So you start with tensor product of these two vector spaces over R, and then you model out by this some module over ID or whatever you call it, and this is the definition of the tensor product, right? And tensor producting over C infinite and mu with C infinite and mu does nothing, right? It's a unit of this monoidal category. So this is isomorphic canonically. So, and it works, of course, on the level of sheaves as well. So this is already a sheaf which is isomorphic with gamma E. So the first property is checked. So this means that there is canonical isomorphism of your radial vector bundle with G0 E, which was also these are the properties. Second, you want to have some kind of prolongation map from sections of E to jets, right? That's another thing we want to have. And so how does it work here? You simply take a section and map it to what? Map it to 1 over 1 times psi, and you take this class. And this is section of what GPjet U, and then you simply map it to the sheafification by this. There's always morphism from pre-sheaf to sheafification, so we just map it, and this gives you one unique linear map JK U, it goes from gamma U to jet U, and this is called cave jet prolongation. In fact, this map is not, it even, if you collect all of them, you obtain sheaf morphism, but it's not C-infinity M linear with respect to this empty triangle, but it's C-infinity M linear with this full triangle. So, but it's not linear C-infinity M linear with respect to the vector bundle module structure like that. Okay, so you have this guy, and the next very important property of jet bundles is that differential operators can be viewed as a linear operators from jet bundle too. So if you start with differential operator on E over U, then there exists a unique C-infinity MU linear map. D hat, it goes from jet U gamma U such that you can write D as the composition of D hat with this jet prolongation. And this is exactly what is true in classical case. So this is the alternative definition of differential operators in the classical case. You first define jet bundles, and then you say the differential operator of cave order is such an operator which factorizes through jet bundle using jet prolongation, right? And in fact, what you can prove that you simply use this argument and wave with heads around that everything is compatible with some module structures and restrictions, etc. And you can then prove that as a vector bundles, this vector bundle of differential operators is really isomorphic to like internal home in the space of graded vector bundles over given manifold from this jet bundle to E. And it's isomorphic. So it's isomorphic canonical, which means that really this sheaf, this vector bundle is representable in this sense. But this is internal home, so it's not just morphism between two vector bundles, but you have to consider all degrees of maps.
So this internal home is between what and what?
This is just internal home in the category of graded vector bundles over a given manifold, and so it's a graded vector bundle. So this whole guy is some graded vector bundle, but it's the same thing as in ordinary geometry. You have vector bundle of linear morphisms between two vector bundles. And last but not least, there are projections. So if you have L less or equal to K, then you can produce a map which basically looks like this. To map these two. And this is well defined because of how the equivalent relations are defined. It's true. So this is a well defined map, and in fact, you can use it to produce map. It goes from jet K E of U, jet L E of U, and these maps are surjective. So luckily, all these nice properties survive the sheafification, which takes some work to do, like because in general, for general sheaves, that's not really true. The surjective maps between pre-sheaves survive the sheafification, but here they do. And in fact, because this is naturally due therefore it defines sheaf morphism, therefore it defines gradient vector bundle morphism. So basically, oh no, I didn't swear. I'm happy. So it goes. This defines vector bundle maps from DK to JLE, and so this is another kind of desired property which you want to have. You want to have this system of gradient vector bundles. And in fact, what you can even do, it was one of the questions last time. You can define what is J infinity, right? Because if you have this kind of system, you can define it using some limits. Yes, limits. You can define Z infinity of E to be the inverse limit of this Z K E, and this is well defined sheaf, because you can calculate limit in the category of sheaves, but you don't have to simplify even, so it's just you can directly write down what is this sheaf explicitly. There is no sheafification involved, but it's of course probably not finitely and free. So it's not a sheaf of sections of vector bundle because it's not finitely generated, but you can define it nevertheless, and it's maybe studied. And of course, then you have projections from this jet infinity E2. Let's say. So you can project elements of your guide to here. Okay. So this basically finishes my talk about the bundles. So this gives you how it's constructed, the reasons why this should be a reasonable definition, because there are some things to be answered. Of course, it would be nice to describe fibers of this gradient vector bundle. So there is a way how to define fibers for gradient vector bundles. I told you last time. It's not that straightforward. It's you pull back the sheaf by some map and you look what that is, but you can construct the fibers. So it would be nice to identify those fibers with something more manageable. Like, look, fibers should be some gradient vector space, which is easy thing. So maybe you can define some gradient vector space of K-order jets. This should be somewhat easy, and then you should identify this vector space within fibers of this guy. I think it should be possible. Then the last time you have comment about Peter's theorem, right? So I looked it up a bit. In principle, it should be true. So there is no reason why not, but I have no proof. I have to go through the proof and try to kind of do it.
What was the question?
The question is that local, in fact, sheaf of local operators is locally sheaf of K-order differential operators. So no, it's not true. I would say every local operator locally is a differential operator of some order. So that is true in the classical geometry, and it should be also true here. And for compact manifolds, even it's true that it's true globally that every local operator is always a differential operator on compact manifolds, and this should be true here. So I should look into that. Probably, I don't know if it's true, and there are some applications of this. So last comment is like 2 minutes, which is exactly what I need. You can use these differential operators to do something with topology. So you can look for special case of gradient vector bundle, which is just n times r, which means that basically this is that the sheaf of sections is the sheaf of just actually sheaf of a manifold. And then you call the corresponding jet bundles and jet the differential operators, just differential operators on M and jet bundles, jet manifold of M. And then you can use differential operators on this gradient vector bundle. So you can look at differential operators here, and you can use it to define topology of this guy. So there is a topology. There's a topology. On CP and U for every open subset. And by quotation marks, I mean that because it's gradient vector space. So what is the topology of on gradient vector space? There is a topology on each component of the gradient vector space. So this has some components. Each of them is ordinary vector space, and there is topology on each of those, making them into Fresnel spaces, which is the nicest topology you can have. So it's kind of complete topology with metric. The metric is complete, and in fact, this you have also product gradient algebra, and all these products between different because you take k component of component multiply, end up in k plus l component of a gradient vector space, and all these operations are then continuous with respect to this topology. And everything is nice. For example, pullbacks are continuous with respect to this topology. In fact, it's something which is called Fresnel sheaf. So some additional condition that you can verify that something is continuous by composing it with restrictions and then verifying the composition with restrictions are continuous things, etc. So it's a very nice unique topology or canonical topology here, making it into gradient vector space, gradient Fresnel space, and why it is useful. For example, you can use this probably. This is what I haven't done, but it should be done, and then you can then prove that very nice thing, which is true for ordinary manifolds and also for supermanifolds. Then everything what is to know about your gradient manifolds is already hidden in the single algebra. So you start with a single algebra of global functions of your gradient manifold, and you are able to reconstruct the whole sheaf out of it. So this is true for ordinary manifolds, for supermanifolds, and it should be also doable for gradient manifolds, and you need this Fresnel topology in the process. So it's important. And of course, jet bundles are useful to handle differential equations, differential operators. So to do some reasonable Lagrangian mechanics on gradient manifolds, you need notion of jet bundles. So I think it's a good thing to have. And last comment, right? I didn't tell you this last time, but it's very important thing that although my description of gradient vector bundles, it's really algebraical using these sheaves, etc. You can always produce a gradient manifold of its total space. So there is some, you can use it to produce gradient manifolds. So there is always a total space of my gradient vector bundle and some projection into my base manifold. And you can, in fact, then reconstruct your sheaf of sections out of this gradient manifold somehow. So it's not really just algebraic thing, but you have some gradient manifolds. So these jet bundles and differential operator bundles, they can be actually used to produce new gradient manifolds, which is always a nice thing because there is a lack of nice examples of gradient manifolds in nature because they are difficult to work with sometimes. But this is a nice way how to produce them. Okay, so that's it.
Thank you
very much.
Short space for questions.
So with my collaborators, we have produced a work where we generalized the notion of jet to the non-commutative case, and despite working with different generic scalar algebra, we only work globally, whereas you work locally and it's everything. Despite starting from different starting points, we end up with a very similar thing. So it's like the support of this. Because,
Yeah,
so it's
nice. So, and of course, this is work in progress. It's not published anywhere. So maybe there are some technical issues which I overlook. Hopefully not.
I can believe it.
Maybe I have a question. You mentioned throughout your talk that you, for some reason, avoided the geometric or more geometric-like perspective on your constructions of jet bundles.
Yes.
Could you comment more on these issues, which or what
No, they are
specific problems would
They are not issues. I just don't know how to approach it using more geometrical way. Like, I have no idea how to do it. Kind of describe this procedure in like starting from a manifold and look at some point and look at some jets of function and
but
point.
you mentioned that you lost some information by viewing.
By evaluating something at the point, yes.
Yes.
For example, you can have sections which are everywhere zero, like their value at every point is zero, but they are non-zero sections. So basically looking at the values of sections, whatever that means, usually loses a lot of data. Like you have vector fields which are zero at every point, but they are non-zero. That's the problem with gradient vector bundles. But you have to, of course, tell what does it mean value of the section at the point.
Maybe another little concern. I don't know what's the actual definition of tensor product in this graded category, but how these two full and empty triangle differ. Then when I imagine this like a tensor product in an ordinary category, you can use linearity or homogeneity to put the factor through the tensor product from one slot to another. And when you're dealing with a graded setting, I would guess that the only difference is the sign.
No, but this is true also in classical case. So also in classical case, the two triangles are different things. It's not the feature of graded setting. This is also true for me. Because there is no relation a priori between the multiplication of function and module structure. They are not related in your. You have to relate it by this. For example, in this degree zero case, you have to impose this relation, and if you impose it, it means that you can take f from first factor to another factor. You only can do it with scalars or scale numbers. If there is tensor product over R, you can do this with scale numbers.
Scalars. Yeah, maybe
but you cannot do it with functions. And if you want to do it with functions, you have to factor this gap here.
Okay.
And these higher things, it's even more complicated. Derivation is quite complicated thing because there are k+1 function here, and then you can move it one at a time to another factor, and you end up with sum of k+1 terms. And this sum of k+1 terms is declared to be zero. This is your relation in your factor and coordinate function. The linearity with respect to function, with respect to scalars, is still working. There's the definition of this tensor over R. You can move scalars, and you can kind of distribute pluses.
Okay. So any other question? If not, we are very happy you made time for this talk.
I'm also happy.
Have you finished your series?
Yes.
So thanks for both of the talks. Thanks. Next time we're looking forward to Mauro's talk. We'll maybe point on some similarities with Jan. So this is the plan for the next week.
thinking, the second way is bringing. Yeah.